What is the relative humidity where water condenses? Water will condense at a relative humidity of 100% because the partial pressure of water in the system is going to be equal to the vapor pressure of the water at that temperature, according to this equation. So we have phi, which represents the relative humidity, and then that's going to be equal to the partial pressure of water divided by the vapor pressure of water. This equation explicitly states that once the partial pressure of the water in the system becomes equal to the vapor pressure of the water at a given temperature, the water will condense because the partial pressure is related to the amount of water in the system. And so once enough water reaches the system, is in the system, then the system will become saturated and the water will condense out. This relationship also tells us that when the partial pressure of the water is equal to the vapor pressure of the water, we have the maximum amount of water in that the system can hold. So if we can find the vapor pressure of the water in the system at a given temperature, then we can solve for the partial pressure of the water because they're equal. And using that partial pressure and the temperature, we can then find the specific volume of the water at that temperature. Because in order for water to condense, it has to be in its saturated vapor state. So we can go to table A2, which is our saturated water table, and read off values for the specific volume. For part 1b, here we can see that our temperature is 50 degrees, our pressure in bar is 0.1235, and then from the table we can read off that the specific volume for our saturated vapor in our system will be 12.03 meters cubed per kilogram. And for part C here at 0.01 degrees Celsius, we see that our saturated vapor pressure is 0.00611 bar, and our saturated vapor specific volume is 206.136 meters cubed per kilogram. So here I've just populated what I just said, and from the specific volume that we've determined, we can find the density or the mass per unit volume of the water vapor at a given temperature for our system. So this is very simple. It's just going to be 1 over 12.036 meters cubed per kilogram, and that's going to give us 83 grams per meter cubed. That's at 50 degrees. At 0.01 degrees, we take 1 divided by 206.136 meters cubed per kilogram, and that's going to come out to 4.9 grams per meter cubed. That is the amount of mass of water vapor that air can hold at 50 degrees and 0.01 degrees Celsius. So now moving on to part 1D, what is the reason why your breath could immediately condense at 20 degrees Celsius but not at 0.01 degrees Celsius? And the answer to this question lies in the conditions of the surrounding atmosphere, because the air coming out of your body is always going to have roughly the same composition and temperature. So its interaction with the surrounding air, which can vary, is what's going to cause condensation or not. Two things that the condensation of your breath mostly depend on are the temperature of the surrounding air and the existing humidity in the surrounding air. Typically, between 2 days of different temperatures, if the humidity is roughly the same, you would see your breath more, you would be more likely to see your breath on the colder day because the air can hold less moisture at a lower temperature. So the added moisture from your breath would cause the partial pressure to increase to the vapor pressure in the air, surrounding air, and that would essentially cause it to condense. And that's why you can see your breath. But there exists a possibility where you have 2 different days, a hot day and a cold day, relatively, and the humidity is much higher on the hot day than it is on the cooler day. In this case, the amount of moisture that you exhale could be enough to reach the saturation point on the warmer day, since it's more humid, but it could not reach that saturation point on the cooler day, even though the air can hold less moisture on the cooler day. So it is possible to see your breath on a 20 degrees Celsius day and not on a 0.01 degrees Celsius day, just based on the relative humidity of the atmosphere on that day. Another way we can express relative humidity is by the ratio of the mass of the water in the air to the ratio of the mass required in the air for condensation. For example, we know that on a warm day, the air can hold more moisture than on a cool day. So say, for example, on a 20 degrees Celsius day, we can dissolve 50 grams of moisture into the air. And on a cool day, we can only dissolve 20 grams. It is possible that if the humidity on the warmer day is, say, 80%, we are, and say every time we exhale 12 grams of moisture, that would be more than enough for the partial pressure of the water vapor to reach the saturation pressure, because 50 minus 40 is less than 12. On a cool day, if you exhaled the same amount of water vapor, 12 grams, but it was only 20% humidity outside, that would be 4 grams of moisture already dissolved into the air. That would only give you 16 grams, which is still less than 20, so your breath would not condense because it did not reach the vapor pressure. And here we're also assuming that mass and the partial pressure of water vapor in the air are directly related enough that we can just think in terms of mass and not pressure.